Why, hello. Today we're going to have our final lecture, which is on section 17.9, which deals with the divergence theorem. Some textbooks actually call it Gauss's theorem also. But we're going to call it the divergence theorem. So we really should have here on the top, divergence theorem. Now what the divergence theorem says is, if you have a simple solid region. Now the way I think about it is if you've got a three-dimensional object and it has all its sides, that you could fill it up with water if you wanted to, and it's going to hold the water, all right, because it's solid, all right. You've got this region which we'll call a solid region, three-dimensional solid, and S is its boundary surface, sort of like think you have a basketball. The whole solid's the whole darn basketball, including the air on the inside, and S is the rubber part on the outside, okay? With positive outward orientation. That means when we do this ds here, our unit normal is directed outward. Then it says if f is a vector field, and we just have to make sure that we have continuous partial derivatives, all right? If that happens on some open region that contains E, then the integral over the surface of what we defined to be the flux before, f dot ds, is equal to the integral over the solid of the divergence of f times dv. So it says, for those of you that aren't too thrilled about doing surface integrals, instead you could do the triple integral over the solid. But the thing to remember is the solid is a closed surface. Like if you have a cube, just to give you some ideas before we do some examples here. Like suppose my E is some cube in three-dimensional space. All right. When we say the integral over the surface of f dot ds, we're talking about you have 6 faces to this thing. When you talk about the integral over s, you have the top, you have this side, you have this side. If you think about it in the back, you've got a side over here, and you got the bottom. So when you do this integral over s of f dot ds, you're talking about an integral over 6 surfaces added up. Notice, for the top, you have a unit normal coming outward. For this side, you have a unit normal going this way. For this side over here, you have a unit normal going out that way. For the bottom, you have a unit normal going out. Then you have another unit normal coming out here and a unit normal over there. But when you go the integral of f dot ds over the surface, we're talking about integrating over all the sides. Because the way I think about it is if I fill it up with water, I need all the sides to keep the water in. But what this theorem says is if you don't want to do that integral over the 6 surfaces and adding them up, that will equal the integral over that solid of the divergence of f just times dv. It's a simple triple integral is what it is. All right, now remembering from before, we defined when this integral of f dot ds, which is your f dot, the unit normal, times the ds, where s is your surface area. We call this the flux. So in your textbook, when you see problems and they say, find the flux of f over the surface, this is what they're talking about. Just reminding you we've done it before. Now, in this one, they want us to verify that the divergence theorem is true for the vector field f on the region E, where f is given as this definition, x squared I plus xyj plus z times k. And E is the solid bounded by the paraboloid z equals 4 minus x squared minus y squared and the xy plane. So what they're asking us to do is first, or second, depending on whatever you want to do, figure out your flux, your integral of f dot ds, and then secondly, integrate over the solid, I like to write it as del dot v, dv, and show that indeed this does equal that. That's how we're going to verify the divergence theorem. And what we're going to do a couple of these today, and I'm not going to go all the way to the bitter end. I'm going to set up the integrals and then say if you put them on your calculator, if you put them on Maple, or if you wanted to be a true trooper, you know, and do it all the way to the bitter end, you would be getting the same answers. And we'll see, sometimes it's easier to do it this way, and other times it's easier to do it this way, and it just depends on which way is the easier way to do it. All right, so I'm going to do it as a surface integral. Now, notice before I even do anything, to get f dot ds, I got to figure out what my surface looks like. Well, I've got an upside down paraboloid. It's z equals 4 minus x squared minus y squared. When x and y are 0, its max is 4. It comes down looking like this. And then they say it's also bounded by the xy plane. Now notice, people, I said I have to be able to fill it up, and I have to have all the sides so that it's going to hold water. I have the bottom, and I have the upside down paraboloid. So if I'm going to call the upside down paraboloid S1 and the bottom S2, when I talk about taking the integral over S of f dot ds, I'm going to have to figure out what the surface integral is over S1, and then also figure out what the surface integral is over S2. And then also remember, before I actually do this, that we have positive outward orientation. So for the top guy, outward, you would have to have unit normals going like that. Okay, outward. But for that bottom guy, how would your orientation go? For the bottom floor, how's my unit normal going to go? Down. Aha. Can anybody tell me what my unit normal would be for that bottom guy? It's going to be minus k, right? Unit normal has to be of length 1, and it's got to be perpendicular. Well, shoot, that guy, if I've got an xy plane and I want to be, this might help better. If you're in the xy plane and you've got this little surface here, a unit normal is going to be going in the z direction but downward. So for that S2, life is going to be pretty good. My unit normal is just going to be minus k. All right, so unfortunately, we've got to figure out both of these and then add them up. So let's do it for the first guy, S1. So I want to figure out what the integral is over S1 of f dot ds. So before I do anything, I got to figure out what's my ds for S1. So let's see. S1 is the upside down paraboloid z equals 4 minus x squared minus y squared. Now, as I recall, if somebody's so kind as to give you your surface by the equation z equals something in terms of x and y, then we learned before that your ds is quite easy. It's minus fx minus fy 1 dx dy. Now, when I do these, I'm going to check to see if my unit normal is pointing in the direction that I want. Okay? So let's see. If my equation is z equals 4 minus x squared, notice my fx is minus 2x, and my fy, partial with respect to y, is minus 2y. So plugging those in, I'm going to get minus a minus 2x is 2x, 2y, 1, dx, no comma there, dy. Now, how do I tell if it's pointing in the right direction? Well, look at your k component. Look at your z component. My z component's positive. If I'm pointing upward, notice your z component for all these guys are positive. I'm pointing in the right direction. If I was pointing in the wrong direction, I'd multiply through by a negative 1, and those guys would be pointing just in the opposite direction, inward. Now we've got to take f dot ds, and that's pretty easy, because here's my f, here's my ds. So f dot ds is you multiply your x components plus your y component plus your z component. So I've got an x squared times a 2x, which is 2x cubed. I got an xy times a 2xy, which is 2xy squared. And then I got a 1 times a z, which is z. And don't forget the dx dy. So we're in our integral for S1 of f dot ds is simply the integral, the double integral of 2x cubed plus 2xy squared plus z dx dy, where we're going over S1. So let me just copy that. I have the double integral over S1 of 2x cubed plus 2xy squared plus z dx dy. Now, I got to get my limits of integration here. So let's go back and look at S1. Okay, so there's S1 showing up right there. A little bit of a problem here, people. Since I'm integrating with respect to x's and y's, I can't be having a z there, can I? So how am I going to ditch the z?
Plug in the z.
Plug in the z. And for the equation for the surface, z is z is 4 minus x squared minus y squared. Now I have to figure out what's my limits of integration. To get my limits of integration, you take the shadow of your surface, since we're integrating with respect to x and y, onto the xy plane. All right, so what does my shadow look like? What does my shadow of that surface onto the xy plane look like? Well, to me, if you take the shadow of that paraboloid onto the xy plane, on the xy plane, z is 0, right? If I plug a z equals 0 in here, I get 0 equals 4 minus x squared minus y squared, or x squared plus y squared equals 4. What does that look like? That's a circle, but now, people, we're not integrating just over the edge. We're integrating over the entire shadow, which is that whole region. And when your region is circular, I mean, we've done this hundreds of times, we're going to use polars. So how are we going to do our polars over that region? I think I'm going to let x be what? Now, am I going to let x be 2 cosine theta or r cosine theta? If I let x be 2 cosine theta, I'm just getting points along the edge. I want to get points on the inside too, so I'm going to let x be r cosine theta. I'm going to let y be r sine theta. And I'm going to let dx dy be r dr d theta. And remember also, x squared plus y squared is equal to r squared, isn't it? Yes, yes, yes. Okay, so, and what's your r going to range from? 0 to 2. And your theta is going to range from 0 to 2 pi. Now, good mathematician's a lazy mathematician. I'm looking here, and you notice I have 2x cubed plus 2xy squared. I'm thinking if I factor out a 2x between those two, if you didn't see this, you'd end up with a cosine squared plus sine squared, which equals 1. But I can make my life a little bit easier. And here, why not factor out a minus? You all with me? So now I'm ready to rumble. Where I see x, I'm going to put r cosine theta. Where I see x squared plus y squared, I put r squared. Where I see x squared plus y squared, I put r squared. Where I see dx dy, I put r dr d theta. And you told me r is ranging from 0 to 2. And theta is ranging from 0 to 2 pi. This one, definitely multiply it out, so you're going to have a 2r to the 4th, 2r to the 4th cosine theta plus 4r minus r cubed dr d theta. But this is a very straight, run-of-the-mill. I did it already, but I don't see any reason to bore you to tears. And I get 8 pi. If you do that out. We could have turned on the calculator, but why take the extra 3 minutes of me punching in the numbers? Definitely you have to do the inside gun first and then the outside one. Okay. You're going to get 8 pi. So what we have so far, coming back here, is, if I can find it, the integral over surface 1 is 8 pi. Now, we also have to do the integral over S2. And let me assume that you don't have such wonderful intuition to see that the unit normal is minus k. Even though if you did, life would be a lot easier, all right? But maybe you didn't see that, all right? You could say that bottom surface is given by z equals 0. So my ds, this is your f of xy. So notice the partial with respect to x is 0 and the partial with respect to y is 0. So if ds is minus fx minus fy1 dx dy, I get ds to be minus 0, which is 0, minus 0, which is 0, 1, dx dy. Now, how is this? Notice I want my unit normal going this way, so I want to have the k component to be negative. By just doing it robotically, I don't have my k component negative, do I? So what am I going to do? I'm going to multiply through by a minus 1. So right now, this is giving me my unit normal this way, but I don't want my unit normal pointing into the interior. We're doing flux, which is flow out of the surface, going this way. So I'm just going to, my ds is not going to be that. It's going to be 0, 0, negative 1 dx dy. And we could have made life a whole lot easier if we said, oh yeah, my unit normal there for S2 is just minus k, and that's exactly what that minus k is. So I go back and I say, okay. Notice my equation for my surface is z equals 0. But when I want to do f dot ds, I take my f right here. You can't see it too well. Let's move it down a little bit. And I take my ds, which I just figured out, which I think if I fold this up, it might help. All right. So we're going to take x squared times 0 is 0. xy times 0 is 0. Z times minus 1 is minus z dx dy. So I'm taking the double integral of minus z dx dy, except I'm integrating with respect to x and y. I can't have a z in there. So I go, okay, for S2, what does z equal? For S2, we're on the xy plane. Z was 0. So God is very good today. Z is 0. And I get a 0. So my flux out of the bottom is 0. Nothing's flowing out. So coming back here, the integral over S2 was 0. So the sum of the two fluxes is 8 pi plus 0, which is 8 pi. And that's using the not using the divergence theorem, just integrating the f dot ds. Any questions so far? Now, since the problem said verify the divergence theorem, we're going to do the second half. Okay? Second half, a lot of times, could be easier, so let's see if it is. All right, let's do it. What do we have here? We want to evaluate the integral, triple integral of del dot f dv. Now, do you remember what del dot f is? Del dot f, okay, doing that right here, also known as the divergence of f, is equal to the partial of the x component with respect to x plus the partial of the y component with respect to y plus the partial of the z component with respect to z. So I'm going to get 2x, partial of that with respect to y is x, partial of z with respect to z is 1. So it looks like I get a 3x plus 1. Okay? So if I want to do my triple integral, it's going to be a triple integral of 3x plus 1 dv. Now what's the volume that I'm going to be integrating over? This. That upside down, that's solid, that's bounded by the upside down paraboloid, and then the xy plane. So it looks to me like my base looks like it's very natural to make it be the circle. So let's integrate with respect to z first. If I take an arbitrary point, so I'm going to go 3x squared plus 1, no x squared, just x, excuse me. 3x plus 1 dz. All right. What's z ranging from? Take an arbitrary z. At the bottom, z is 0. And at the top, what's my z on the paraboloid? It's 4 minus x squared minus y squared. Now, my base looks like a what? Looks to me like it's a circle, right? So I think I can make life a lot easier if I look at my base in the xy plane. It's just the circle we did it a few minutes ago. X squared plus y squared equals 4. So I think I'm going to use x is r cosine theta, y is r sine theta. And so instead of having dx dy here, I'm going to go to 0. And notice we have 4 minus x squared plus y squared. Notice you could write that as minus the quantity x squared plus y squared. So it would be 0 to 4 minus r squared dz. Oh, I need to change that x, but I'll do that in a minute. I'll replace x with r dr d theta. We'll have the r range from 0 to a radius of 2. Theta going from 0 to 2 pi. And all that's left in this integration before I do it, I'll replace x with r cosine theta. And again, this integration, it's not bad. It's straight, sines, cosines, and r's and that type of stuff. You just have to be a bit careful when you do it. I went ahead and did it. and miraculously I got 8 pi, which is exactly what we got doing it the other way. Now, if you're out in the trenches and you do it, are you going to do it both ways? No, you're going to do whichever way is the easiest. Okay, whichever way is the most obvious. Okay, any questions? Well, that's number 1. All right, so let's go on and look at number 2. Verify the divergence theorem is true for this vector field. And the reason I chose this one is that it's a sphere. It's a sphere. So let me do it the first way first. Notice the divergence theorem says the integral over the surface of f dot ds is equal to the integral over the volume of del dot f dv. So I'm going to do this one first, because if someone asks me to compute this, and I say, oh, this equals this, this probably is a little bit easier. So let's do that. Let's do it this way first. So first let's figure out what is the divergence del dot f. It is the partial with respect to x of my x component plus the partial with respect to y of my y component, which is y, plus the partial with respect to z of my z component. So it's just 1 plus 1 plus 1, which is 3. So I'm taking the triple integral of del dot v, which is 3 dv, over that unit sphere, whose equation is x squared plus y squared plus z squared is less than or equal to 1. Well, I think most of you would agree that I could factor out the 3. Well, if you have your integrand of 1 there, and you're integrating over a triple integral of your volume of 1 dv, what does this piece turn out to be? What your volume is, right? So that's going to be 3 times the volume of the sphere. Does anybody know the formula for the volume of a sphere? Last time I looked, it was 4/3 pi r cubed. What's the radius of this particular sphere? The equation of a sphere is x squared plus y squared plus z squared equals r squared. So r squared is 1. So the radius of this sphere is just 1. Yeah.
Is it p squared?
P squared?
It isn't x squared plus y squared plus z squared.
Oh, you could write it as rho squared if you want. Right, rho squared, right. But the rho squared is 1, right? And so the radius is 1. So if I plug a 1 in here, my 3's cancel, and my answer would just be 4 pi. The volume of a sphere is 4/3 pi times its radius squared. And you could write it as x squared plus y squared plus z squared equals r squared, where r is the radius, or rho squared is fine too. So as you can see, this one, the triple integral is quite easy. I didn't even have to do it because I knew that if you integrate over 1 dv of a solid, you're just getting the volume of the solid. And since it's a ball, I know that its volume is 4/3 pi r cubed. Now let's do it the other way. The other way is not as easy. I want to figure out the integral of f dot ds for this sphere, which means that I have to represent my sphere parametrically. Don't be telling me that the surface is given by x squared plus y squared plus z squared equals 1. That's the surface of the sphere. You can't solve for z nice and patly. You with me? If you do, you're going to get z equals plus or minus the square root of 1 minus x squared minus y squared. If you wanted to, you could do S1, which is given by z equals plus square root of 1 minus x squared minus y squared. Figure out what that is with your minus fx minus fy, 1 dx dy. Then your S2 would be given by z equals minus the square root. I don't want to be doing that because those derivatives are awful. I mean, it's doable, but they're quite hideous. You know, the derivative of this with respect to x, have fun. It's that to the 1/2. So you've got to bring that down, leave this alone, to the minus 1/2 times a negative 2x. So just your x component would be a negative 2x over square root of 1 minus x squared minus y squared. Eek, I don't want to do that. So instead, how am I going to represent this ball, this unit ball? And my spheres are terrible, but you're used to it at this point. Well, that one's not too bad. Okay, there's my ball, all right? How can I represent that parametrically? It's a ball. It's a sphere. If you have a sphere, use spherical coordinates. How are my spherical coordinates given by? If you go back and look it up, you'll see that your x is equal to rho cosine theta sine phi. Y equals rho sine theta sine phi. And your z is given by rho cosine phi. Now what are theta and phi? You might remember, if you have a point in three-dimensional space, rho is the distance that you are from the origin. Phi is the angle. Once you draw your little, think of it as your little radius going from the point to the origin, the angle that this little bar makes with the positive z-axis is called phi. And if you drop this down into the xy plane, your theta is the angle that you're making with the positive x-axis. So what do phi and theta range from? Well, you might remember phi goes from 0 to pi. And what does theta go from? 0 to 2 pi. And if all of these points are on the sphere, a sphere of radius 1, what does rho equal? If you're on the sphere, x squared plus y squared plus z squared equals 1, its radius is 1, so rho is equal to 1. So I can make rho be 1. So here, if rho is 1, all these little pieces for rho drop out. And so therefore, my parametric representation for this sphere is r equals, now what's my x component? It's cosine theta sine phi times I plus sine theta sine phi times j plus cosine phi times k. This is my x, this is my y, this is my z. Now, when it's given parametrically, let's just review for a minute to remember why this is true. If you've got a surface, you know, when you're breaking it up into a bunch of delta s's, this little vector right here would be the partial of r with respect to theta times d theta. This little vector right here is the partial of r with respect to phi d phi. Now remember, if you take the cross product of those, these are vectors, by the way, so they should have little bars on top. Remember, that produces a vector that's normal to both, but whose length gives us the magnitude of the area of the parallelogram determined by those two vectors. So if I go partial of r with respect to theta, cross with partial of r with respect to phi, and multiply it by d theta, just factor that out. This is giving me a vector perpendicular to both, whose length is equal to the area of that little area. And that area right there is just your ds. And so this is equal to your unit normal times ds, or you could write it as just ds with a bar on it, because that's what ds with a bar means, a vector that's perpendicular to the surface, whose length is the length of that little unit normal. So what we have to do here is we've got to figure out what is the partial of r with respect to theta, and what's the partial of r with respect to phi. And then we've got to take the cross product of those and simplify it, and then tack on d theta d phi, and that will give us our ds. So that's a little bit painful, but I think we better do it. So to get the partial of r, so coming back here, remembering, if you have your surface given parametrically, your ds is just going to be the partial of r with respect to theta crossed with the partial of r with respect to phi, and then just tack on your d theta d phi. So let's see, what is the partial of r with respect to theta? Well, let's see. It's going to be, derivative with respect of cosine theta is minus sine theta, and then we just leave sine phi there because it's like a constant, I, plus the partial of this with respect to theta is cosine theta sine phi j. Partial of this with respect to theta is good, it's just a 0. Now we're going to differentiate with respect to phi. So if I'm differentiating with respect to phi, I get cosine theta cosine phi. And you've got to be real careful you don't write a theta as a phi or vice versa. Partial of that with respect to phi is going to be sine theta cosine. I'm differentiating with respect to phi, so I get cosine phi again. And the partial of that with respect to phi is minus sine phi. Now if I'm going to go r theta cross with r phi, think of this as your I, j, k, and here are your components lined up. So this is going to give us, let's see, when I go, this is a little bit bloody, but we can do it. You're going to eliminate the row in the column that I is in, and we go this times this minus that times that. So that's going to give me, when I go this times this, I get cosine theta times sine phi times minus sine phi. So I get minus sine squared phi cosine theta I. All right, because I went this times this, minus 0 gives me nothing. Plus, or we can go minus j times, now eliminate the row and column j's, and we're going to go this times this, which gives me minus times minus is a plus sine theta. Sine phi times sine phi is sine squared phi. Minus, when I go this times that, that's good, I get 0. Plus k times, eliminate row and column that k is in, when I go this times this, let's see what I get. I get sine theta, so I have a minus sine squared theta, sine phi, cosine phi, minus, and when you go this times this, let's see, we have cosine squared theta, sine phi, cosine phi. Not a pretty problem. So let's see what we have here in terms of r theta cross r phi. I get for my I minus sine squared phi cosine theta times I, plus for my j I get a minus sine squared phi sine theta. Now I could just write the k, but people, look at the k for a second. Look at this. Look at the k part. You have minus sine squared phi, sine phi, cosine phi, minus cosine squared theta, sine phi, cosine phi. I'm going to factor out a minus sine phi, cosine phi. And that would give me sine squared theta plus cosine squared theta. And what's sine squared plus cosine squared? 1. So my j part's pretty cool. It's just plus minus sine phi cosine phi k. Now let's check. Is my unit normal pointing in the right direction? You don't want to do it, but you really should. Let's check. What does my surface look like? What's my surface? Oh, it's a ball. My surface is a ball. Okay. My surface is a ball. So if my surface is a ball, how is my unit normal supposed to be pointing? Outward. Remember, divergence theorem says all your unit normals have to be going outward. Well, let's look at that one right there. At the top, phi is 0, and theta can be anything, okay? Because your phi, well, in fact, why don't we take this one right here? But right here, the angle that you're making with the z-axis pointing this way is going to be pi over 2, and my theta is 0. So this little guy, I want him pointing that way. So I want the x component to be positive. Well, look, see, if I let theta be 0, cosine of 0 is 1. Sine of pi over 2 is 1. Uh-oh, my x component is a negative 1. But I want this pointing in the positive direction. I have these guys pointing in, and I want it pointing outward. So what do I have to do? I have to multiply by a negative. So my ds in reality is just going to multiply through by a negative. So it's going to be sine squared phi cosine theta I plus sine squared phi. Oh, I messed up there. I don't think that's a sine phi there. Let's go back and go back. Let me look here. sine squared phi sine theta. This is a theta here. It's very easy to mess those up. So I have minus sine squared phi sine theta j, there should be a j there, plus a sine phi cosine phi k. Bit tedious. And then we have to multiply that whole thing times d phi d theta. Now we're ready to do our dot product, which isn't too bad. We want to figure out what is the double integral of f dot ds. So I got to pull out what f is, which I'll do that in a second. Is it underneath here? Yes. Okay, there's my f right there. And I need my ds, which I have right here. Okay, and when I do that, I want to figure out what is f dot ds. I get this x component, which is x, times sine squared phi cosine theta, plus this y times sine squared phi sine theta, plus this z times sine phi cosine phi. And we want to integrate that with respect to d theta d phi, except unfortunately, if we're integrating with respect to d theta d phi, I got an x, a y, and a z showing up there. So what do I have to do yet? I have to plug them back in. So coming back here, for x, I'm going to put cosine theta sine phi. For y, I'm going to put in sine theta sine phi. And for z, I'm going to just put in cosine phi. Which looks horrendous, but you know, I'm not going to combine similar terms and do all that. But if I go d theta d phi, what's theta ranging from, we said? 0 to 2 pi. And phi's ranging from 0 to pi. Now you know what's going to happen. You're going to get like a sine cubed. You'll get like a sine cubed in there, and you're going to have to siphon off a sine and write it as 1 minus cosine squared. You'll get a sine squared, and you'll have to write it as 1 minus cosine 2 theta over 2. But if you do, I already went through, or better yet, put it in a computer algebra system like a TI-89 or a 92 or on Maple, and miraculously you get 4 pi, which is exactly what we had before. So the point is this. Unfortunately, the guys in the TV studio are going to have a take-home in which they're going to have to do this, all right, do it both ways to justify that they're same. But after you leave this course, if you had to do the flux out of a ball, I think you would use the divergence theorem. The one thing I did it like in 3 lines, this one I put half of you to sleep, all right? So it was a lot of work, a lot of work. So now, we don't want to verify the divergence theorem. We want to use the divergence theorem to calculate the surface integral. This is called the flux, f dot ds. That is, calculate the flux across S of this function over this surface. So we're not going to be doing it over the surface. This is a box that has vertices plus or minus 1, plus or minus 2, plus or minus 3. So what does that look like? All right. You're going to go, your x's go all the way from 1 to minus 1. Your y's are going to go all the way from 2 to minus 2. And your z's are going to go all the way up to 3 down to minus 3. I'm not too good at drawing it in 3D, so let me do it in 2D first. If I just look at the side of the box in the xy plane, your x's are going from 1 to minus 1. And your y's are going from 2 to minus 2. And that's just looking at it in the xy plane, right? Then we're going to look at it, if we look at it, this is the y and this is z. Z is going from plus 3 to minus 3. 3 to minus 3. And again, your y's are going from plus 2 to minus 2. So the cross section looks like this. So in reality, I've got this wonderful box. It might look something like that. And you've got your x, y, and z axis coming around like this, and we're going to be going, you know, out to plus 1 for x, plus 1 minus 1, plus 2 minus 2 for y, and plus 2 minus 2 for z. So what we're going to do first of all is we're going to say this isn't bad. We're told that the integral over s of f dot ds. Notice doing this would be a real pain. This thing has 6 surfaces. So you'd have to do the integral over s1 plus s2 all the way up to s6. You have 6 different unit normals to compute. You know, that would be a bit painful. But instead, we're going to say this is equal to the integral over the solid of del dot f dv. So what we want to do first of all is we want to figure out what's del dot f. Well, del dot f is the partial with respect to x of the x component plus the partial with respect to y of the y component, that's a cube there, plus the partial with respect to z of the z component. So that's going to give me, let's see, partial with respect to x gives me 2x z cubed. Partial with respect to y is 2x z cubed. Partial of that with respect to z is 4x z cubed. So we're going to be integrating 2 to 8, 8x z cubed. And this is easy. This is a box. So it's very simple. Your z, I got the wrong one here. Here it is. Your z is, what's your z ranging from? From minus 3 to 3. And then you can go with respect to x or with respect to y. I don't really care. We want to go with respect to y. That shadow onto the xy plane is just going, the y is just going from -2 to 2. And the x's are just going from -1 to 1. And this is fine. We're integrating with respect to x, y, and z. So my integram can be in terms of x, y, and z. We could pop this onto the TI-83, but or not the 83, but the 92. Take my word for it, we will get 0. It's not a hard integral to do. It's just simple polynomial is what it is. And this is a whole lot easier. Instead of having to do an integral over 6 surfaces, we do one triple integral and we're done. Let's do this one. Use the divergence theorem to calculate the surface integral of f dot ds, that is the flux of f across s, of the following. So again, we have to figure out what del dot f is. So that's the partial with respect to x of x squared y, plus the partial with respect to y of our y component, which is xy squared, plus the partial with respect to z of 2xyz. And this is giving me, let's see, 2xy plus 2xy plus partial of that with respect to z is 2xy. So it looks like I have 6xy. Okay. Now, what does our solid look like? Well, let's see if I can figure out what that is. S is the surface of the tetrahedron bounded by, now my plane is x plus 2y plus z equals 2. Let's see if I draw that. Let's draw that plane here. If I'm looking at x plus 2y plus z equals 2, when y and z are 0, x is 2. So that's right there. When x and z are 0, y is 1. And when x and y are 0, z is 2. So my tetrahedron, tetra means 4. Can we all see? You have the top is right here. And then your planes, x equals 0, y equals 0, z equals 0, are your coordinate planes. So, you have, the xz plane, the yz plane, and the xy plane as your faces. So now, if you did the flux integral of f dot ds, have fun. You've got to do 1, 2, 3, 4 integrals, because you've got 4 sides. But if we just go the integral over del dot f, the divergence, we figured out that was 6xy dv. All we have to do is figure out what are our limits of integration for that integral. And then we'll be done. So I think what I'm going to do is I'm going to just set up my limits of integration. If I take a point in the xy plane, I'm going to be integrating with respect to z first. What is z ranging from? Well, it starts out at 0. It ends up on the plane. Well, the equation for the plane was x plus 2y plus z equals 2. So if I solve for z, I get z equals 2 minus x minus 2y. So my z is going from 0 to 2 minus x minus 2y. How do I figure out my limits of integration for xy? I take the shadow of my surface onto the xy plane. I want to integrate over that in the xy plane. I find it much easier just to draw it in the xy plane, so I'll do that real quick. We're crossing the x-axis at 2, and we're crossing the y-axis at 1. So the region I want to integrate over is here. Notice the equation of this line, since you're on the xy plane, z is 0, you could just let z be 0, and the equation is going to be x plus 2y equals 2, or y equals, I'm going to divide through by 2 and get 1 minus a half x if I solve for y. Notice y-intercept is 1, so that's your b, and your slope is down 1 over 2, it's minus a half. So I guess I'll integrate with respect to y first, and then with respect to x. Y is ranging from 0 to 1 minus a half x. And then if I sum all those up, x is ranging from 0 to 2. So instead of doing 6 integrals, I can do 1, and take my word for it, the answer turns out to be 2, is that 2/5? Let me see. We're doing number 8. Page, 2 pi over 3, I apologize. How can that be 2 pi over 3? What is that? That's not it. That's right here. Yeah, it is 2/5. Turns out to be 2/5. Okay? All right. Let's do another one. Next one I want to look at in terms of setting it up is, suppose I have the surface. The equation is x to the 4th I minus x squared z squared j plus 4xy squared z. They want me to figure out that, but the divergence theorem says that that integral is equal to the triple integral of the divergence of f times dv. So what we've got to do first of all is just figure out what the divergence is. That's pretty easy, so I'll do that first. My divergence of f, which you could also write that way, is partial with respect to x of x to the 4th plus partial with respect to y of minus x squared z squared plus partial with respect to z of 4xy squared z. So it looks like I get 4x cubed. That with respect to y, that one's easy. That's a 0. And the partial of that with respect to z is 4xy squared. So my divergence is going to be 4x cubed plus 4xy squared. Now let's figure out what the surface looks like. Well, my surface is the solid bounded by the cylinder x squared plus y squared equals 1. That looks like that. Normally we can draw that, extend it up and down. Our book usually is nice and just makes us extend it up. Z equals 0, that's down here, that's the xy plane. And what does z equals x plus 2 look like? What's that? That's a plane. Now can you think about it? The plane, normally z equals x plus 2, you would draw it in the xz plane. So when x is 0, z is 2. When z is 0, x is negative 2, so you're back here. And then you're going to drag it along. Drag it along the y-axis. And you can see it going like that. So what you're going to be doing is you're cutting this cylinder, and you're going to have like, let's see, when x is 0, z is 2. So when x is 0, z is 2. It's going to come there. When x is 2, z is 4. So it's going to be coming down like this. Can you see? You're sort of like cutting it. So the solid that we want to integrate over has this is its bottom, this is its top, and this is its sides. Now, have fun to do this. I mean, you guys would be just thrilled. If I wanted you to do the integral over s of f dot ds, you got 3 sides. You got the lateral side, so you got to represent that cylinder parametrically. You got to do this top, and you got to do this bottom, and you're going to have 3. Now notice, for the surface integral here, your unit normal's got to be going up that way. For this bottom, your unit normal's going this way, and for the lateral sides, your unit normals have to be pointing out. But that would be a painful problem. We'd be here for about 15 minutes, which I don't think we want to do. So instead, the integral over all 3 surfaces added up with outward unit normals of f dot ds is equal to the triple integral of del dot f dv. We just figured out del dot f was 4x cubed plus 4xy squared. Okay, and let's look at it. What do you think you want to integrate with respect to? I think I'm going to make my base be the xy plane, right? And I think I'm going to integrate with respect to z first. So I think I'm going to do integral 4x cubed plus 4xy squared dz dx dy. So what's z ranging from? Well, z, if you take an arbitrary point in that region, z is ranging from 0 to the plane. Well, the plane's given by z equals x plus 2. I have it right there. Z equals x plus 2. So we're going to go from 0 to z equals x plus 2. Now, what's my base? Oh, you guys tell me. What's my base? It's a circle. So what kind of coordinates do we have to use? Polar. So I think, and it's x squared plus y squared equals 1. My base in the xy plane looks like this. So I guess I have to let x equals r cosine theta, y equals r sine theta, and dx dy equals r dr d theta. And also remember, x squared plus y squared equals r squared. But now notice, we're almost done here. If I set this up, notice, before I rewrite this, it's 0 to x plus 2, but x is now going to be r cosine theta. Notice I could factor out an x. So we can replace, we're going to be going from 0 to r cosine theta. X is going to be 4r cosine theta. X squared plus y squared is r squared, dz, r dr d theta. What's my r ranging from? From 0 to 1. My theta from 0 to 2 pi. Definitely you want to multiply that r back in there, but when you go through and do that whole thing, we get 2 pi over 3. That's what our answer is going to be. And it's 1 integral instead of 3. Okay, we're all doing okay?
That first integral should be a plus 2.
Oh, r theta, right, because it's x plus 2. So I'll put 2 plus there, absolutely. Because coming back here, it was x plus 2, absolutely. I need the plus 2, thank you. Okay, let's just set up one more. Do I need one more or am I done? I think I'm done, aren't I? That was the last one. My goodness. All right, before we quit, section 17.10 has no problems, so don't think like, oh my goodness. But if you look in section 17.10, they're very kind that they sort of review everything we've done in chapter 17. We started out with the fundamental theorem of integral calculus. We said if you were integrating from a to b of f prime of x dx, the antiderivative of f prime was f, so we evaluated f at b minus f at a. Notice here you're integrating from a to b, but all we had to do in calculus 1 was evaluate f at the endpoints, at the borders, and took the difference. Then in calculus 3, we learned sort of the fundamental theorem of integral calculus' form for line integrals. If you wanted to integrate along a curve, instead of f prime, we had the gradient of f dotted with dr. That would just be the scalar function f evaluated at the final point minus the initial point. Then we learned a form of Green's theorem. Green's theorem, notice, is only good for two-dimensional force fields or vector fields. Your f, notice, just has a p component and a q component. It does not have a k component. And notice your your region D is in the xy plane. And what Green's theorem said is if you want to find the line integral around this simple closed curve, it will be the same as the integral over the region of the partial of q with respect to x minus the partial of p with respect to y. So we were equating an integral over a region to the integral over the surface. Now in 3D, Green's theorem has a different form called Stokes' theorem. It says if you want to integrate over the surface of the curl of f dot with ds, that's over the entire surface. You could instead integrate the line integral of f dot dr, but you have to make sure that your orientation is if your little guy walks along the edge and he has this little cap on his head, the cap is the unit normal. As he walks with that cap on his head, his left arm has to be always facing into the region. Now, we're not going to do it, but if you wanted to, if you had a function that just had an x component and a y component, but no k component, and you evaluated this here, you will find out that Stokes' theorem with functions that have 0 for their k components turns out to be Green's theorem. So Stokes' theorem is just Green's theorem in 3D is what it is. And then finally today, we didn't prove, but I gave you what's called the divergence theorem. And it says if you want to integrate the divergence of f dv over this solid, you will get the same answer as you integrate over the whole entire surface of f dot ds. Just remember though, divergence theorem, or it's also known as Gauss theorem, only applies to solids. I think about it as if I wanted to fill that up with water, I have to have all the sides included to hold the water in. And notice your unit normals on all the sides are always directed outward. But if you do that, if you sum up all these faces, it will be the same as this one simple integral. What you need to do for our last class is look over pages 1163 to 1168. 3 to 9 the odds and 13 and 15 are nice problems. Do you have time to do them all? No. But you have time to do some, all right? And then the chapter review, if there's certain topics that you need extra practice on, these are good ones to look at. So like if you forgot how to do a line integral, you forgot how to do a surface integral, they're nice ones to look at just to review. What you might very well do is say, how would I do that? Again, let me just caution you. Some of you have been very good and come to see me. You're looking at the Student Solutions Manual, and sometimes they do things a little bit wacky. You that are at home, if you don't understand something that's in the Student Solutions Manual, email me. I will write it out in a different form to explain to you what they're doing, because sometimes they skip steps or they don't really explain their motivation and they do things a little bit weirdly, and you try to do monkey see, monkey do, and you don't really understand. It's been a delight. If I can ever be of service to you in the future, don't hesitate to call me, and I'll see you later. Bye-bye.